Hello everyone. In this video we will learn how to find length of a curve defined by the graph of a function or using a function. So we will assume that we have a function, f is a differentiable function, and we also assume another condition that f prime is continuous. Well, you will notice why we assume that condition on the interval a. Then, we can simply define the curve y equals to f of x is defined. Basically, that is the graph of the function, yes, and we want to find its length. Well, on this interval a to b. Okay, so so we are going to have something like this, and well, from a to b, we have this curve going from there to there, and then we want to find its length. What we do here is that, well, we chop this interval into n equal subintervals, and well, for each point down there we find a point on the curve. Now we approximate each arc there using a straight line segment. Okay, this one's like that. And then we know that if we add the length of arc length line segments, and well, we assume the n of them are there, so you add 1 to n. Then if we make this subinterval smaller and smaller, or in other words increase the number of these guys, this should give us the arc length that we are looking for, yes? But what is the length of this line segments? Let me just zoom in one of these guys like that and say that this is the starting, that's the end point. We approximate that arc by this line segment. Here, this is, say, xi, this is xi plus 1, then obviously this will be f of xi, and then this will be f of xi plus 1. Now, what is this guy here? What is the length of that? So just by turning this to in the right triangle, you see that here is xi plus 1 minus xi, which we denoted by delta x, and up there is going to be f of xi plus 1 minus f of xi. Well, we will write that as delta y. Now, you have a right triangle with two right edges to be delta x, delta y. Then hypotenuse is what we are looking for, and that will be given by the Pythagorean theorem. And this is delta y squared, delta x squared plus delta y squared under the square root. So let me just rewrite this part. So we are looking for this sum. Here, if I factor out delta x, what I will get is 1 plus delta y over delta x. I am factoring out delta x squared, and then well, outside I will get delta x, square root of delta x squared, which is just delta x. Why I'm trying to write this thing, recall that we had this Riemann sum, which was of the form limit of n goes to infinity of sums of a function. You choose any point from the ith subinterval times delta x. I goes from 1 to n. This, if that function is continuous, must be equal to integral a to b, definite integral a to b, hx dx. Okay, I have delta x as I have all the other parts there. Now I have to figure out what is that h of xi star. Well, that square root 1 plus, those are clear what we have to do. The problem here is that what is this delta y over delta x, which then we have to square it. This is f of xi plus 1 minus f of xi over xi plus 1 minus xi. This quotient, by a mathematical theorem or fact, must be equal. It's called mean value theorem. Derivative of that function f at a point in the subinterval xi to xi plus 1. Okay, so in other words, what we are having here is limit of n goes to infinity I from 1 to n root 1 plus f prime at xi star squared and then times delta x. Well, here this xi star would change depending on the function and each subinterval, but well, there are theorems saying that, okay, so if your function here f prime 1 plus f prime square under the square root is continuous, which we assume that f prime is continuous, so this will be continuous. This is going to be given by integral a to b of that function, which is f prime x then squared plus 1 under the square root dx. That is the formula you need to know for the arc length of the curve given by the graph of a function. So I will write it by L. Let's apply this in some example. Here, find the length of this curve. Here the function is x to the power 3 over 2. So then the function, yes, and the derivative is going to be 3 over 2 x to the power 1 over 2, 3 over 2 minus 1, and it is continuous on the interval 1 to 4, yes, obviously. Then the length, arc length, is given by 1 to 4 of root 1 plus f prime, which is 3 over 2 x to the power half squared dx. Okay, so 1 to 4 of root 1 plus 9 over 4 x to the power half squared is x dx. So we wrote this arc length as this integral. Now, can we evaluate that? And so that from this point on depends on how many tricks, techniques you know for integration. So this is linear function under the square root, so that can be integrated by substitution, and that will give me du is equal to 9 over 4 dx, and well, that will give me Okay, so 4 over 9 integral of root u du. So I multiplied that to the other side and so on. How about the limits of the integral? If x is 1, then we have u is 1 plus 9 over 4 times 1, which will give us 13 over 4. If x is equal to 4, then u is 1 plus 9 over 4 times 4, which will be 10. Okay, so this will be 13 over 4 to 10. Now, well, this is u to the power half. We can integrate it using just simple power rule, 1 over half plus 1, u to the power half plus 1, and then go from 13 over 4 to 10. So that will give us 2 over 3, and we multiply outside, we get 8 over 27, and this is u to the power 3 over 2. Okay, now let me just apply it. 10 to the power 3 over 2 minus 13 over 4 to the power 3 over 2. I'm not expecting you to be able to simplify all the work here, but you can go a little bit more. I will leave it like that, and that is the arc length that we were looking for. Okay. Sometimes the curve, so remark, sometimes the curve is given in terms of x in terms of y. So arc length of a curve y, before y equal to f of x. Now if x equal to g of y for values of y between a and b is equal to, so in that case you can do different things. For example, I would say that you change x and y variables, and then you repeat what we had up there, and that will give you integral from a to b. This time you're integrating y variable, okay? 1 plus g prime y squared under the square root dy. So that would be our formula if the curve is given by a function like that. Okay, let's do one example here as well. Find our arc length of the curve. This root of 2 minus y squared. So here gy is 2 minus y squared, the square root. Here then we can find g prime y. G prime here means that you differentiate with respect to y, and that will be negative 2y over 2 root 2 minus y squared, which will give us minus y over root 2 minus y squared. And then that will tell us that L is integral from 0 to 1 root 1 plus negative y over root 2 minus y squared dy. And if we simplify this, this will be, actually we can find the common denominator there, plus y squared. Negative y squared is y squared, and this will be 2 minus y squared. Everything is under the square root. These two cancels, and we get root 2 from the numerator. I'll put it outside. 1 over 2 minus y squared dy. Okay, so if I factor out well, this is just a simple integral. Well, you can do different ways. For example, I can use y equals to root 2 say sine theta. From there, dy is going to be root 2 cosine theta d theta, and the limits will turn to u is y, sorry, y is 0. That will imply that theta is 0. Y is 1 will imply that sine theta is 1 over root 2, which is theta is pi over 4. So this will be pi over 4, 0, root 2 cosine theta d theta over 2 minus 2 sine squared theta. Okay, and that way you simply see that, okay, so numerator and denominator will cancel each other, and you will get just 1, which is then root 2, just theta go from 0 to pi over 4, and that is just root 2 pi over 4 minus 0. And that is what we were looking for. Okay, just quick wrap up is that when you have a curve defined by a function like that, and you're looking for the arc length of the curve for values of x between a and b, you differentiate the function, square it, add 1, find the square root of that, then integrate. The same way will go if you have x equal to gy, and then you integrate this other one and then find the arc length.